In 1998, two teams of astronomers independently set out to confirm something they already believed to be true. They wanted to measure how quickly the expansion of the universe was slowing down. Not whether it was slowing down. That part they were sure of. Gravity pulls everything together, and the universe had been expanding since the Big Bang. So, of course, the expansion should be decelerating. The only open question was by how much. Whether there was enough matter out there to eventually reverse the expansion entirely, or whether the cosmos would coast outward forever, slowing all the while, getting colder and emptier as the billions of years piled up. To answer that, they went looking for exploding stars. Specifically, a type of stellar explosion called a Type 1a supernova. These explosions are remarkable tools for astronomers. Every single one of them detonates at roughly the same intrinsic brightness. That makes them what astronomers call standard candles. If you know how bright something truly is, and you can measure how bright it appears from here, you can calculate exactly how far away it is. The dimmer it looks, the farther it is. And across billions of light years, these exploding stars act like mile markers on a cosmic highway, telling you precisely how far out the universe extends and how fast it has been expanding across deep time. The results came back, and they were wrong in the worst possible way. Not wrong in a way that pointed to a measurement error or a miscalculation. Wrong in a way that pointed to something real, something out there in the universe that nobody had expected to find. The distant supernova were too faint. Not dramatically so, but unmistakably so, beyond any statistical noise. And in astronomy, a standard candle that looks dimmer than it should be can only mean one thing. It is farther away than it should be. The universe had not been slowing its expansion. It had been speeding it up. Something was pushing the galaxies apart with increasing force, overcoming all the gravity of all the matter in the observable universe, and winning. Who led one of those teams from the Lawrence Berkeley National Laboratory, later described the experience of checking and rechecking the data, going back over every assumption, every calibration, every possible source of error. The chain of reasoning was long and strange, he said, and they were reluctant to trust what it was telling them. The other team, led by Brian Schmidt and with Adam Rees doing much of the analysis, arrived at the same answer through the same reluctance. They had expected to watch the universe slow down. Every single piece of data they had fit a universe that was doing the opposite what those two teams had found in 1998 was one of the most profound and disorienting discoveries in the history of science. They had stumbled onto the dominant ingredient of everything that exists, a component of the cosmos that is not matter, not radiation, not anything that can be seen or felt or weighed or tested directly, but a strange, invisible energy spread uniformly through all of empty space, quietly pushing the structure of the universe apart with a force that grows more dominant with every passing billion years. We gave it a name. We call it dark energy. And the name is, in a very honest sense, an admission of total ignorance. Dark because we cannot see it. Energy because it appears to do something. But what it actually is, where it comes from, why it has the strength that it does and not some other strength entirely, none of that is understood. Before we go any further, it helps to sit with the proportions of the universe for just a moment because they are genuinely humbling. Everything you have ever seen, every star that has ever shone, every planet that has ever orbited one, every galaxy that has ever formed, every single atom in your own body and every other body on Earth, all of that ordinary matter adds up to approximately 5% of the total contents of the universe. Another 27% or so is dark matter, a different mysterious substance we have never directly detected, but whose gravitational effects on galaxies and clusters are unmistakable. And the remaining 68%, by far the largest share of everything that exists, is dark energy. We live in a universe whose overwhelming majority is invisible to us. Everything we have ever seen, studied, mapped, measured, and touched is a thin, bright surface floating on top of a vast, dark ocean that we do not understand. There is a remarkable historical wrinkle to all of this. The force those astronomers discovered in 1998 had, in a sense, been accidentally predicted and then thrown away nearly a century earlier. When Albert Einstein published his general theory of relativity in 1915 and then developed it into a full description of the universe in 1917, his equations kept producing an unstable cosmos. They told him the universe must be either expanding or contracting, but could not simply sit still. This was deeply uncomfortable. At the time, the overwhelming consensus, including Einstein's own, was that the universe was static, eternal, and unchanging. Stars were where they were. The cosmos was a fixed thing. So Einstein did something that he would later deeply regret. He added a new term to his equations by hand, a kind of built-in repulsive pressure filling all of empty space, just enough to counteract gravity and hold everything in place. He called it the cosmological constant. A little over a decade later, the astronomer Edwin Hubble demonstrated that the galaxies were not standing still at all. They were flying apart. The universe was expanding. Einstein's extra term was unnecessary, an embarrassing patch job applied to a problem that had not actually existed. He reportedly called the cosmological constant the biggest blunder of his life, and he removed it from his equations. Then, in 1998, his blunder came roaring back to life. Because what those two supernova teams had found was precisely what a cosmological constant would produce. A fixed energy built into empty space, the same everywhere and at all times, gently but persistently pushing space itself apart. The discarded correction turned out to be the most important term in all of cosmology, the leading theoretical candidate for what dark energy actually is. The one that maps most naturally onto Einstein's cosmological constant is the energy of the vacuum, the energy of empty space. This sounds paradoxical. How can nothingness have energy? But quantum physics tells us that truly empty space is not truly empty. At the very smallest scales, the vacuum seethes with fluctuating quantum fields, particles and antiparticles flickering into existence and annihilating each other so rapidly they can never be directly caught. This constant quantum activity gives empty space what physicists call vacuum energy, a baseline energy that belongs to the fabric of spacetime itself. A cosmological constant is, in this picture, simply the measured value of that vacuum energy, and it should, in principle, be calculable from our quantum theories. Here is where the story takes a deeply uncomfortable turn that physicists have been quietly living with for decades. When theorists try to calculate the vacuum energy from first principles using quantum field theory, the answer they get is not close to what we observe. It is not slightly off. The theoretical prediction and the measured value disagree by a factor of 10 raised to the power of 120. That is a 1 followed by 120 zeros. It is the largest discrepancy between theory and observation in the entire history of science. Physicists sometimes refer to it bluntly as the worst prediction ever made. What this means in practice is that we can measure dark energy. We can see exactly what it is doing to the universe. We just have absolutely no idea why it has the gentle value it has, rather than being unimaginably stronger. An energy so overwhelming that no atom, no molecule, no galaxy, no structure of any kind would ever have had a chance to form. The fact that the universe exists at all in its current form, with galaxies and stars and planets and us, is, in some deep sense, a mystery bound up in this discrepancy that we cannot explain for a long time. Despite that mystery, there was at least a settled picture of where dark energy was carrying us. If it is a true constant, fixed forever at the same value, then the fate of the universe follows a clear, if bleak, trajectory. The expansion continues. Over hundreds of billions of years, the galaxies beyond our local group are swept away faster and faster, eventually crossing what cosmologists call the cosmic event horizon, the boundary beyond which nothing, not even light, can ever reach us. Those galaxies disappear from the observable universe entirely. One by one, the stars exhaust their hydrogen fuel and die. The white dwarfs cool to black dwarfs, lightless cinders. The neutron stars slowly evaporate. Over almost incomprehensible timescales, even black holes lose mass to Hawking radiation and evaporate away. New stars stop forming because the raw material has been consumed and scattered. The universe grows darker, colder, emptier. The temperature approaches absolute zero. Motion ceases. The lights simply go out, one after another, and stay out. This is the fate cosmologists call the heat death, or sometimes the big freeze. It is not a violent ending. It is a quiet one, an endless frozen darkness in which nothing ever happens again. That was the ending we believed we knew, and it was built on one assumption that nobody had seriously questioned. The assumption that dark energy is constant, that the force we measured today is the same force that existed 10 billion years ago and the same force that will exist 10 billion years from now. A true cosmological constant, Einstein's term, unchanging and eternal. That assumption, it turns out, is testable, but testing it requires something almost absurdly ambitious. It requires mapping the expansion of the universe, not as it stands today, but as it was at every moment across the whole of cosmic history. It requires building a three-dimensional chart of the cosmos, so vast and so precise that you can read the history of the expansion, written into the positions of the galaxies themselves, billions of years into the past. That is exactly what a collaboration of more than 900 scientists from over 70 institutions around the world set out to do. Using an instrument called the Dark Energy Spectroscopic Instrument, known as DESI. The instrument is mounted on the Mayall telescope, a 4-meter mirror that has been watching the sky from the summit of Kitt Peak in the Arizona desert since the 1970s. Kitt Peak sits at an elevation of roughly 2,100 meters, high enough to place the telescope above much of the atmospheric interference that blurs observations from sea level, and far enough from city lights to give a genuinely dark sky. The mountain is also home to one of the largest collections of optical telescopes in the world, making it one of the great centers of modern astronomy. What DESI adds to this aging but capable telescope is an extraordinary piece of engineering. At the heart of the instrument is a circular focal plane packed with 5,000 tiny robotic positioners. Each robot holds a single optical fiber thinner than a human hair. Every 12 to 20 minutes, those 5,000 robots swing simultaneously into a new configuration, each one pointing its fiber precisely at one specific galaxy chosen from a pre-planned target list. The light from 5,000 galaxies at once, collected and channeled down those fibers into a bank of instruments that spread the incoming light apart into its constituent colors, producing a detailed spectrum for every single galaxy simultaneously. A galaxy's spectrum is a fingerprint. It contains dark absorption lines at specific wavelengths, produced by specific atoms in the galaxies, stars, and gas. And crucially, the position of those lines shifts depending on how fast the galaxy is moving away from us. The more the universe has expanded since the light left that galaxy, the more those lines have been shifted toward the red end of the spectrum, stretched by the ongoing expansion. Astronomers called this redshift, and the amount of redshift tells you not only the distance to the galaxy, but the moment in cosmic history when that galaxy emitted its light. A galaxy with a large redshift is a galaxy seen as it was billions of years ago, when the universe was younger, smaller, and denser. DESI's 5,000 fibers, operating night after night, year after year, have been building a map that is not just a map of space, but a map of time, over its planned 5-year survey. DESI set out to measure precise distances to tens of millions of galaxies and quasars, weaving them together into the largest three-dimensional map of the universe ever constructed, reaching back 11 billion light-years from Earth. To grasp what that scale actually means, consider that our entire Milky Way galaxy, a structure roughly 100,000 light-years across and home to somewhere between 100 billion and 400 billion stars, would appear as a single invisible speck within this map. Not a small speck, an undetectable one. Every galaxy in the survey is itself a vast city of stars, comparable to or larger than our own, and DESI tracked tens of millions of them. For the most distant regions of the map, ordinary galaxies become too faint to observe. So DESI extends its reach using quasars, the blazing active cores of distant galaxies powered by supermassive black holes in the process of devouring enormous quantities of gas. A quasar can outshine its entire host galaxy by factors of thousands, making them visible across almost the full width of the observable universe. In the spectra of the most remote quasar, DESI reads the faint imprints of intervening clouds of hydrogen gas strung out across billions of light-years, a technique that pushes the map further still toward epochs when the universe was only a small fraction of its present age, but a map of where the galaxies sit is only the first part of the puzzle. The real power of DESI lies in something more subtle, a faint statistical pattern embedded in the galaxy distribution that most people have never heard of, called the baryon acoustic oscillation. To understand what this pattern is, you have to go back almost to the very beginning. In the first few 100,000 years after the Big Bang, the universe was a searingly hot, opaque plasma of particles and radiation. Matter and light were locked together in a dense, glowing fog. Through that fog, pressure waves rippled outward from every dense spot, expanding spheres of slightly compressed gas moving at roughly 57% of the speed of light. These were sound waves in the most literal physical sense, propagating through the primordial plasma the way ordinary sound propagates through air or water. Though on a scale that staggers imagination, approximately 380,000 years after the Big Bang, the universe cooled to a critical threshold. The electrons and protons that had been bouncing light around began to combine into neutral hydrogen atoms. The fog cleared. Light was suddenly free to travel, and the pressure waves, deprived of the radiation pressure that had been driving them, froze in place wherever they happened to be at that moment. Like a bell struck once, and then immediately muffled, the sound waves stopped. But they left behind a permanent imprint in the distribution of matter, a very slight excess probability of finding one galaxy at a specific distance from another galaxy, equal to how far those ancient sound waves had traveled before they halted. This characteristic distance is called the sound horizon. It is approximately 490 million light-years across. And here is why this matters so much. That frozen scale is fixed. It was set in the first 380,000 years of cosmic history, and it has been the same everywhere in the universe ever since. It is a built-in ruler, a standard scale encoded into the structure of the cosmos itself. By measuring how large the baryon acoustic oscillation pattern appears at different distances from us, and therefore at different epochs in cosmic history, DESI can work backward to determine exactly how fast the universe was expanding at each of those moments. It is, as one astronomer described it, like using the echo of the Big Bang as a tape measure stretched across 11 billion years of cosmic history. When DESI turned that ancient ruler on the sky and traced the history of the expansion across the largest sample of galaxies ever assembled, the data by itself was consistent with the old picture. On its own, DESI's map fit a universe ruled by a constant cosmological constant, a fixed energy in empty space, exactly as the simplest version of Einstein's revived idea would predict. If that had been the whole story, there would have been nothing new to report. But cosmologists never study the universe with a single instrument in isolation. The power of modern cosmology comes from combining independent measurements, each one probing a different aspect of the same underlying reality and checking whether they all agree. DESI's galaxy map was combined with 3 other major probes of cosmic structure: the cosmic microwave background, the faint afterglow of the Big Bang, still filling the sky in every direction, carrying detailed information about the early universe, the brightness measurements of distant Type 1a supernova, and the subtle gravitational lensing of background light by foreground matter. Each of these probes is calibrated independently. Each one constrains the behavior of dark energy in a different way. When DESA's three-dimensional map was layered together with all of those other measurements, the comfortable picture began to crack. The combined dataset was no longer best explained by a dark energy that holds perfectly steady. The numbers fit slightly, but consistently better if dark energy is not a true constant at all, but has been slowly, gradually fading across the history of the universe, losing strength little by little as the eons passed. The force that everyone had assumed was fixed and eternal might instead be evolving. The first hint of this emerged from DESA's earliest data release in 2024. Hints in physics are common. Most of them dissolve as more data arrives. Statistical fluctuations that looked interesting for a moment and then regressed to the noise. But this one did not dissolve. When DESI released a second, larger dataset in 2025, drawing on 3 full years of observation and spanning more than 14 million galaxies and quasars, the signal grew stronger rather than weaker. As the survey neared completion in 2026, charting tens of millions of galaxies with the full 5 years of data still being analyzed, the same whisper kept returning in every independent analysis. Dark energy may not be what we thought. The universe may not work the way we believed it did. Will Percival, a professor at the University of Waterloo and one of the leaders of the DESI collaboration, described the shift with measured care. The simplest explanation for what they were seeing, he said, was beginning to change. The standard model of cosmology might need to be modified to make all the different measurements agree with one another. Another DESI scientist, Andrew Fontrabera of the Berkeley Laboratory, put it more directly. Perhaps, he said, the universe is telling us that it is more complicated than we ever thought. Mustafa Ishak, an astrophysicist at the University of Texas at Dallas, and another leader of the project, framed what this would mean for the long term. What they had always believed about the universe, simply expanding faster and faster until it was nearly empty, was now back on the table. The expansion could one day stop. The universe could collapse. Take a moment to let the strangeness of that sentence settle. For decades, the collapse of the universe was crossed off the list of plausible futures. The accelerating expansion made it seem essentially impossible. Gravity could never overcome a relentlessly strengthening push. And now, because that push might be weakening rather than strengthening, the ending that was considered settled is no longer settled. In fact, the full range of possible endings for the universe has suddenly reopened, and it is worth thinking through each of them carefully, because the differences between them are not minor variations on a theme. They are completely different fates, separated by almost unimaginable differences in character. Think of it as 3 distinct futures, each one hinging on the behavior of dark energy in the billions and billions of years to come. The first future is the one we believed in for decades. If dark energy is a true cosmological constant, if it holds steady at precisely its current value forever, then the expansion simply continues, compounding on itself endlessly. The galaxies beyond our local group drift away and eventually cross the cosmic horizon, disappearing from our observable universe for good. Stars exhaust their fuel and die. New star formation stops when there is no fresh gas left to collapse. White dwarfs cool to black, lightless cinders. Neutron stars and black holes hold on for unimaginable timescales before eventually fading through quantum mechanical processes. The universe grows steadily colder, emptier, more uniform, approaching thermal equilibrium. The technical term for this ending is heat death. The common name is the Big Freeze. It is not a violent death. It is the quietest possible ending, a fade to cold black over timescales that make the current age of the universe seem like a brief prologue. The second future is far more violent. It requires not just that dark energy be something other than a constant, but specifically that it be something that grows stronger over time. Its outward push intensifying as the eons accumulate. If this were happening, the acceleration of the universe would not merely continue, it would run away. The rate at which space expands between any 2 points would increase without limit, and at some point, the force driving that expansion would become strong enough to overcome not just gravity between galaxies, but gravity within galaxies, tearing them apart. Then the force would overwhelm the gravity-binding solar systems together. Stars would be ripped away from their planets. Then the electromagnetic forces binding molecules and atoms would give way. Matter itself would be shredded. And in the final, catastrophic moments, even the fabric of space-time would be torn to pieces. Physicists call this scenario the Big Rip. In some models, it could arrive in as little as 20 billion years. It is death by dismemberment, the entire content of reality pulled to pieces all the way down to its most fundamental threads. The third future is the one that Desi has quietly put back on the table. It requires dark energy to be not steady and not growing, but fading, losing its strength gradually as the cosmos ages. If this is what dark energy is doing, then a remarkable reversal becomes possible in the deep future. As the outward push weakens, the force that has dominated the cosmos for the last 5 billion years begins to falter, and waiting underneath it, patient and permanent, is gravity. Gravity never goes away. It just loses the contest against the stronger force. If dark energy weakens far enough, gravity could win back the upper hand. The expansion would slow, it would stop, and then, for the first time since the Big Bang, it would reverse. The galaxies that have been flying apart for 13 billion years would begin ever so gradually to fall back toward one another. And once that long fall begins, there is no natural stopping point. The contraction starts slowly, almost imperceptibly at first, but gravity is relentless. The universe would contract faster and faster. Galaxies, growing closer, would begin to interact, merge, collide. The night sky would fill with light. Temperatures would rise throughout the cosmos as matter compressed. Everything that the expansion had scattered thinly across such vast distances would come crashing inward. The universe would grow hotter and brighter and denser with every passing epoch. And in the final moments, everything, all the matter and energy and space and time that has ever existed, would be compressed into a single point of infinite density and temperature. The same kind of point from which the Big Bang emerged. Cosmologists call this the Big Crunch. A universe that spent its entire history flying apart would gather everything back up at the end and crush it all together, finishing the longest story imaginable in precisely the place where it began. Some cosmologists have wondered whether the story would even truly end there. In certain theoretical frameworks, the Big Crunch is not a terminus, but a bounce. The compressed point immediately exploding outward again into a new Big Bang. A new universe carrying no memory of what came before. This idea of a cyclic cosmos, eternally collapsing and rebounding, has a certain strange elegance. A universe with no beginning and no end, only an endless succession of expansions and contractions, each cycle generating new physics, new structures, new possibilities. It is speculation stacked upon speculation, but it is speculation grounded in real physics, in loop quantum cosmology and ekpyrotic models that take the geometry of higher dimensional space seriously. But here is what is more unsettling than any one of those three endings. It is not the freezing or the tearing or the crushing. It is the fact that if dark energy is genuinely changing, then we have lost the ability to predict which of those endings awaits us. A constant dark energy is, by definition, predictable. A force that never changes will do tomorrow exactly what it does today. You can project it forward across all of future time with confidence. You can calculate the fate of the universe as clearly as you might calculate the trajectory of a thrown ball. But a dark energy that evolves is a completely different kind of thing. Its behavior in the future depends on a dynamical equation we do not know. It could keep fading. It could level off. It could reverse and begin growing stronger again. It could do something stranger still that no model has yet imagined. Consider what this means in the most concrete terms possible. For the last several decades, if you had asked a cosmologist how the universe ends, they could have given you a coherent, detailed, scientifically grounded answer. The expansion continues, the stars die, the lights go out. The cold takes everything in the end. It was bleak, but it was solid. It was built on well-tested physics and confirmed observations. And now, because a force whose nature we have never understood may also be doing something we never expected it to do, that answer is no longer available. We cannot tell you how the universe ends, not because we have failed to measure it, but because the very force that will decide is behaving in a way that our theories cannot yet follow into the future. We are driving toward the end of everything, and the road ahead has vanished from the headlights. It is important here to be precise about what has and has not been established, because this is exactly the kind of story that is easy to tell badly. The original discovery of the accelerating universe is not in doubt. It was confirmed beyond any reasonable question by Perlmutter, Schmidt, and Rees, who shared the Nobel Prize in Physics for the discovery in 2011. The acceleration is real. Dark energy is real, in the sense that something is causing the expansion of the universe to speed up. That much is as solid as anything in modern physics. What is genuinely uncertain, what these new DESI measurements have put back into question, is whether the force driving that acceleration is perfectly constant, or whether it is slowly changing. That may sound like a narrow technical distinction. It is anything but. It is the difference between a universe whose future we can extrapolate with confidence and a universe whose future has become an open question again. It is the difference between knowing the ending of the story and realizing that you may have been reading the wrong story all along. And the evidence for the change, while suggestive and growing, has not yet crossed the threshold that physicists set before they will call something a confirmed discovery. The standard in physics is demanding. A result must achieve what is called 5 sigma, meaning the probability of it being a chance fluctuation in the data is less than 1 in 3,500,000. The evidence for evolving dark energy from Desai's combined analysis sits at somewhere between roughly 3 and 4 sigma, depending on which datasets are combined and how. This is in the range of what physicists call a strong hint. It is not nothing. In fact, it is quite striking. But the history of particle physics and cosmology is littered with 3 sigma hints that looked compelling for a year or 2 and then faded back into the noise as more data arrived. There is a second complication that the DESI scientists themselves have been transparent about. The signal depends significantly on which catalog of supernova measurements is used in the combined analysis. There are several independently assembled catalogs of distant Type 1a supernova, each one compiled by a different team with slightly different selection criteria and calibration methods. When Desai's galaxy map is combined with one of those catalogs, the evidence for evolving dark energy looks fairly compelling. When it is combined with a different catalog, the evidence nearly disappears, leaving a picture that is consistent with a constant dark energy after all. The answer, in other words, depends on which supernova you trust. George F. a highly respected cosmologist at the University of Cambridge, has made the case that the entire effect might be explained away by a small systematic error in one of the supernova datasets, a calibration offset of only a few hundredths of a unit of brightness between nearby and distant explosions. If that offset exists and is corrected for, the signal for changing dark energy may simply dissolve. This is exactly the kind of subtle, hard-to-detect error that has derailed exciting results before in the history of science, and it is not yet settled whether such an error is present, to their considerable credit. The DESI team has been genuinely rigorous about all of this. They employed a technique called blinding, deliberately concealing their own results from themselves while they were analyzing the data, specifically to prevent their expectations and hopes from subtly biasing the analysis toward a preferred answer. This kind of intellectual discipline is hard to maintain. The temptation to look at your own results is almost physical. They resisted it, and they have been the first and most insistent voices saying that what they have found is a question, not yet an answer. A powerful and tantalizing question that the next generation of measurements should be able to resolve, because those next generation measurements are already underway. The Euclid Space Telescope, launched by the European Space Agency, is designed specifically to study the expansion history of the universe with extraordinary precision, mapping the shapes and positions of billions of galaxies across a significant fraction of the sky. The Vera Rubin Observatory in Chile, equipped with the largest digital camera ever built for astronomy, will conduct the legacy survey of space and time over 10 years, cataloging billions of galaxies and tens of thousands of supernova with a thoroughness and precision that dwarfs any previous survey. These instruments will produce data of a quality and quantity that should make the current ambiguities either clearly real or clearly artifacts. If the signal is real, if dark energy truly is evolving, those surveys will make it unmistakable. The evidence will cross the 5 sigma threshold. The anomaly will show up consistently across independent datasets. The picture will become clear. If it is not real, the new data will show a universe consistent with a constant dark energy, and the DESI signal will turn out to have been one of those tantalizing false hints that the history of science is full of. Either outcome is a genuine result. Either the standard model of cosmology is broken in a fundamental way, or it survives one of its most stringent tests. Science, done properly, is designed to find out. But there is a deeper dimension to this story that the statistics and the error bars cannot fully capture. It has to do with when we are living. We exist at a very particular and, in some sense, privileged moment in cosmic history. Dark energy only began to dominate the expansion of the universe about 5 billion years ago. Before that, in the universe's younger, denser phases, the energy density of matter and radiation was high enough to keep gravity in control, and the expansion was actually slowing. If you had lived in the universe as it was 8 or 10 billion years ago, you would have measured the expansion and concluded, correctly, for that era, that gravity was winning. You would have had no hint of what was coming. Look far enough into the future, and the situation reverses completely. If the expansion continues, the galaxies beyond our local group will drift further and further away. Their light increasingly redshifted, their recession velocity eventually exceeding the speed of light relative to us. Not because anything is traveling faster than light through space, but because the space between us and them is expanding so rapidly, they will cross over the cosmic horizon and become permanently invisible. And not just invisible, causally disconnected. No signal will ever again pass between us. To any beings alive in that distant epoch, looking up at the night sky, the universe would appear to contain only the Milky Way and its nearest neighbors. Every other galaxy would be gone, not destroyed, just unreachable and undetectable. They would have no way of knowing that trillions of other galaxies once shared their universe. They would have no evidence of the Big Bang expansion. The entire history of cosmic structure we can read today would be invisible to them. We may be living in one of the only windows in all of cosmic time when these questions can even be asked. When the universe is old enough for observers to have evolved, but young enough that the evidence of its structure and history is still written across the sky in legible light. To be here now, with the instruments and the mathematics to read that story, is a coincidence of timing that is genuinely remarkable. And we are doing exactly that, asking the largest questions our species has ever posed. Right at the moment when the answer has started to shift beneath our feet. Michael Levy, the director of the DESI project, has described all of this in terms closer to wonder than to dread. Whatever dark energy ultimately turns out to be, it is going to shape the future of our universe. And there is something quietly astonishing in the simple fact that we can stand on the surface of one small, ordinary, rocky world, aim our instruments at the sky, and begin to seriously engage with a question of that magnitude, not as a philosophical exercise, not as speculation, but as a testable scientific inquiry with real evidence accumulating in real time. What does it mean that the force governing the fate of everything might be changing? It means, at minimum, that our model of the universe, the standard model of cosmology that has served us extraordinarily well for decades, the model that correctly predicted the abundances of the light elements formed in the Big Bang, that predicted the precise pattern of the cosmic microwave background, that explained the large-scale structure of the galaxy distribution may be incomplete, not wrong in its core structure, but missing something. Some physics that we do not yet have the equations to describe. A dynamical ingredient in the dark energy that the cosmological constant, in its simplicity, does not capture. There are theoretical frameworks that naturally produce a dark energy that changes over time. The most studied is called quintessence, a name borrowed from Aristotle's concept of a fifth fundamental element filling the cosmos. In quintessence models, dark energy is not a fixed property of empty space, but a scalar field, a physical field spread through the universe that can have different values in different places and at different times. Just as the Higgs field gives mass to particles, or the inflaton field is thought to have driven the exponential expansion of the very early universe. A scalar field has dynamics. It rolls down a potential energy landscape, changing its value over time. And as it changes, the effective dark energy it produces changes with it. If the quintessence field has been slowly rolling downhill for billions of years, its push on the cosmos would gradually weaken, which is exactly what DESI's data may be suggesting. Other frameworks are even more radical. Some theorists have proposed that general relativity itself, Einstein's description of gravity and spacetime that underlies all of modern cosmology, may break down or behave differently on the very largest scales of the universe. In such modified gravity theories, what we call dark energy is not a separate substance or field at all, but a consequence of gravity itself behaving differently at cosmic scales than it does locally. There is currently no experimental evidence that general relativity is wrong on any scale. It passes every test we have ever applied to it with extraordinary precision, but no one has yet tested it directly on the scale of the observable universe. DESI and its successors are doing exactly that. There is also the possibility, discussed more and more seriously in recent years, that the apparent signal of evolving dark energy is not a property of dark energy at all, but a symptom of something wrong with how we model the universe. The standard cosmological model treats the universe as perfectly uniform, perfectly smooth on the largest scales. In reality, the universe has structure, enormous voids, and dense filaments and clusters of galaxies. Whether that structure on intermediate scales could somehow mimic a changing dark energy in the statistical analyses remains an active area of research. It is another possible explanation that the data cannot yet rule out. What is clear is that we are in one of those rare and exciting moments in science when a foundational assumption is being seriously challenged by actual measurements, not by theoretical speculation, not by philosophical argument, but by photons collected on real nights, by a real instrument pointed at real galaxies, scattered across 11 billion years of cosmic history. The universe is doing something with these measurements. It is either confirming our model or beginning to break it. Either outcome will be a landmark. One will vindicate decades of careful theoretical work. The other will open one of the deepest new problems in the history of physics. And if we are being honest about the strangeness of where we find ourselves, this question, how does the universe end, is one that no species anywhere in the cosmos can answer by looking forward. You cannot observe the future. You can only measure the past and the present, and try to build a model accurate enough that you trust its We have been building that model, refining it, testing it for a century, and it has worked remarkably well. The fact that it may now be telling us something unexpected is not a failure of science. It is science functioning exactly as it should, following the evidence wherever it leads. Even when it leads somewhere uncomfortable, the galaxies are still racing apart right now. At this moment, as you hear these words, the expansion is continuing. The dark energy is doing whatever it is doing, constant or changing. In every cubic meter of empty space, in every direction from where you are, in the emptiness between the planets of our solar system, in the vast gulf between our sun and the nearest other stars, in the spaces between the stars of the Milky Way, in the hundreds of millions of light years between galaxies, in the billions of light years of near nothingness that make up the bulk of the observable universe. The force is everywhere, and it is silent, and it is deciding right now how all of this ends. For a few decades, we believed we knew the answer. The expansion would continue. The stars would die. The lights would go out one by one and stay out. It was a settled story. And then we built the largest map of the universe ever made. 900 scientists, tens of millions of galaxies, 11 billion light years of data. And the map whispered back something we did not quite expect. That the most important assumption in our story of how everything ends might need to change. We are a young species on an ordinary planet. We have been looking at this sky for no more than the barest fraction of its history. For a little while, we allowed ourselves the comfort of believing that we had worked out how the final chapter goes. And the universe, quietly, through the accumulated light of hundreds of millions of galaxies, has begun to suggest that we may not have. That is not a cause for despair. It is a cause for curiosity. We have better instruments coming, better data arriving every year. Euclid is mapping the sky. Vera Rubin is counting galaxies in the southern hemisphere. New catalogs of supernovae are being assembled with greater care. The question of whether dark energy is constant or evolving will be settled, or at least much better constrained, within the next decade. The answer may vindicate everything we thought we knew, or it may open a door onto new physics that nobody has yet imagined. What is certain is that the question is real, the measurement is real, the uncertainty is real, and the universe has not yet told us how it will die. The force that will decide is out there right now, in every empty space in the room around you, in every gap between the stars, in the vast dark gulfs between the galaxies, silently doing something. And for the first time in a long time, we have to admit that we are no longer certain what that something is. If this kind of exploration is what draws you back, if following the science as it actually unfolds, rather than after the fact, is something you value, then staying with it, staying subscribed, leaving a signal that this kind of content reaches you, matters more than it might seem. Every piece of support helps keep the exploration going, because the story of dark energy is not finished. It will not be finished for years. The next chapter will be written by the instruments currently opening their eyes to the sky, by the data currently being analyzed in laboratories and offices around the world, by the minds currently working through the theoretical implications of a universe that may be more complicated than we assumed. When the answer comes, it will be one of the most important things any science has ever learned. And the fact that we are here asking the question, at the exact moment in cosmic history when it can be asked, is a strange and remarkable thing. The universe began approximately 13.8 billion years ago in an event of unimaginable density and temperature. It has been expanding ever since, for all of that enormous time, through the formation of the first stars and galaxies, through 10 billion years of stellar births and deaths, through the emergence of rocky planets and chemistry and biology, and eventually minds capable of asking questions. All of that history, and the entire future to come, rests on the behavior of a force that remains, at its core, a mystery. We called it dark energy because we did not know what it was. We still do not know, but we are measuring it more precisely with every passing year. And every measurement is a step closer to understanding. The largest map of the universe ever built has given us the strongest evidence yet that something may be changing in the fabric of reality at the grandest scale. Whether that something is a new field in physics, a modification to our theory of gravity, a subtle error in our measurements, or something we have not yet conceived. The path to finding out runs through more data, more instruments, more carefully analyzed light collected from the depths of the cosmos. That path is being walked. The next few years will tell us whether the ground we thought we were standing on is solid, or whether it has been shifting all along beneath our feet, carrying us toward an ending that is stranger and more open than we ever imagined. For now, the only honest answer to how the universe ends is that we do not yet know, and that, after decades of believing we did, is one of the most interesting things science has said in a very long time. To understand why this moment in cosmology feels so charged, it helps to step back and appreciate just how recently we assembled the picture that is now being questioned. The standard model of cosmology, sometimes called lambda-CDM, after its two main invisible ingredients, the cosmological constant lambda, representing dark energy, and cold dark matter, is a framework that was essentially assembled in its current form between the 1980s and the early 2000s. Before 1998, the cosmological constant had been abandoned for 70 years following Einstein's own dismissal of it. The universe was expanding, gravity was slowing it down, and the future was a matter of whether the expansion had enough momentum to continue forever, or whether matter density would eventually reverse it. Those were the two options on the table. Then the supernova teams found the acceleration, and the whole picture was redrawn in the space of a few years. The acceptance was not instant. Scientists are skeptical by professional necessity, but the evidence was too strong to resist. By 2003, a landmark dataset from the Wilkinson Microwave Anisotropy Probe, a satellite that mapped the cosmic microwave background in extraordinary detail, had confirmed the broad outlines of lambda-CDM with compelling precision. The proportions of the universe, roughly 5% ordinary matter, 27% dark matter, 68% dark energy, emerged from the data with remarkable clarity. The age of the universe, its geometry, its expansion history, the physics of the very early universe, all fit together within the lambda-CDM framework with a consistency that was hard to argue with. Subsequent observations only deepened the confirmation. The Planck satellite, launched by the European Space Agency in 2009 and producing its definitive results over the following years, measured the cosmic microwave background with a precision that was staggering. Its data constrained the parameters of lambda c dm to fractions of a percent. The large-scale structure of the galaxy distribution, mapped by the Sloan Digital Sky Survey and other programs, agreed with lambda CDM predictions. The baryon acoustic oscillation signal appeared in the galaxy data, exactly as theorists had predicted it would, based on the Big Bang physics. For a period, it seemed as though cosmology had achieved something that physicists in other fields could only dream of: a complete, consistent, precisely calibrated model that agreed with essentially everything we could measure. And yet, there were always tensions. Small discrepancies between different measurements that refused to fully resolve. The most persistent and widely discussed of these is the Hubble tension, a disagreement in the measured value of the Hubble constant, the parameter that describes the current rate of expansion of the universe. When astronomers measure the Hubble constant using the cosmic microwave background, projecting forward from the very early universe through the lens of lambda CDM, they get one number. When they measure it directly using local distance measurements, the cosmic distance ladder built from Cepheid variable stars and supernovae, they get a different number. The two values disagree by roughly 8 to 10%, a discrepancy that has persisted and in some analyses grown as both measurement methods have been refined. If the discrepancy is real and not a product of systematic errors in either measurement, it suggests that lambda CDM is not quite right. Something is missing or something is wrong. The DESI signal fits within this broader context of unease. It is not the only place where the standard model is showing strain. The Hubble tension, the DESI dark energy evolution signal, and a handful of other smaller anomalies are all pointing in the same general direction. Lambda CDM may be an excellent first approximation, but there may be physics beyond it that we have not yet identified. Whether all of these tensions resolve to a single new ingredient or represent several different problems is not yet clear. But the accumulation of anomalies is precisely what tends to precede scientific revolutions. Not every anomaly leads to a revolution, of course. The history of science is full of tensions and discrepancies that turned out to be measurement errors, calibration problems, or statistical fluctuations. The lesson of 3 sigma hints dissolving is a real one, and serious scientists keep it in mind. But some anomalies really do persist, really do grow, really do force a fundamental rethinking. Astronomers in the early 20th century noticed that the orbits of the outer planets did not quite match Newtonian predictions, and for decades that was considered a possible measurement problem. Eventually, it was explained by the planet Neptune, predicted by calculation, and then found exactly where the mathematics said it should be. The anomaly was real. The explanation was a new component of the solar system nobody had catalogued, on grander scales. The evidence for dark matter itself began as an anomaly. The Swiss astronomer Fritz Zwicky noticed in 1933 that the galaxies in the Coma cluster were moving far too fast to be held together by the gravity of the matter he could see. The cluster should have been flying apart. He proposed an unseen mass, what he called dunkel materie, dark matter, holding it together. His colleagues were largely skeptical. The idea sat on the margins for decades. Then Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies in the 1970s and found the same problem everywhere they looked. Galaxies were rotating, as if wrapped in invisible halos of mass that extended far beyond their visible stars and gas. The anomaly was universal. The explanation was dark matter. Today, the evidence for dark matter is so overwhelming from so many independent directions that its existence is not seriously doubted. Even though nobody has yet directly detected a dark matter particle in a laboratory, the history of physics teaches that when multiple independent measurements point toward the same anomaly, the anomaly tends to be real. And when an anomaly is real, something genuinely new is waiting on the other side of it. Dark matter was waiting on the other side of galactic rotation anomalies. Dark energy was waiting on the other side of supernova brightness anomalies. What might be waiting on the other side of dark energy evolution anomalies is one of the most exciting open questions in fundamental physics. The theoretical possibilities are genuinely diverse. Among the most studied alternatives to a pure cosmological constant is a class of models involving dynamical scalar fields, the quintessence models mentioned earlier. These fields are similar in concept to the Higgs field, which was theorized in 1964 and experimentally confirmed in 2012 with the discovery of the Higgs boson at the Large Hadron Collider. A quintessence field would pervade all of space and carry energy that varies as the field evolves over cosmic time. In its simplest forms, a quintessence field slowly rolls down a potential energy hill, gradually losing energy as it does so. This would cause the effective dark energy density to decrease over cosmic time, producing exactly the pattern that DESI's measurements hint at. What makes quintessence particularly interesting, theoretically, is that it potentially connects cosmology to fundamental particle physics in ways that a pure cosmological constant does not. A cosmological constant is, in a sense, not really a physical entity at all. It is just a property of empty space, a number that you have to put into Einstein's equations. A quintessence field, by contrast, is a real dynamical entity. It participates in physics. It can potentially interact with other fields, be produced in high-energy collisions, leave signatures in experiments far smaller than the universe. If dark energy is a quintessence field, then understanding it might require not just better telescopes, but better particle detectors. It would be a bridge between the very large and the very small in physics. Another set of alternatives falls under the heading of modified gravity. General relativity describes gravity as the curvature of spacetime produced by mass and energy. It has passed every test we have subjected it to with extraordinary precision, including tests in the strong field regime around neutron stars and black holes, tests of gravitational wave emission from merging compact objects, and tests of the speed of gravitational waves themselves. But the tests have been done in specific physical environments, on scales of the full observable universe, on the scale of the cosmic expansion itself. General relativity has never been directly tested against an alternative. It has only been tested in the sense that observations are consistent with it. Modified gravity theories that agree with general relativity on small scales, but deviate on cosmic scales, are not excluded by existing tests, and some of them predict a cosmic expansion history that differs from what lambda-c dm predicts, potentially producing a signal in the galaxy. Distribution that looks like evolving dark energy even when there is no actual dark energy to evolve. Distinguishing between quintessence and modified gravity observationally is not easy. Both can produce similar expansion histories, but they differ in their predictions for the growth of large-scale structure. The way that matter clusters into galaxies and galaxy clusters over time. Future surveys like Euclid and Vera Rubin are designed specifically to measure both the expansion history and the growth of structure simultaneously, with enough precision to break the degeneracy between different theoretical models. The combination of these measurements should allow cosmologists not just to detect whether dark energy is changing, but to begin to narrow down what it actually is. There is also the possibility that what we are seeing is not a problem with dark energy or gravity at all, but a problem with our understanding of the very early universe. Some of the tensions in modern cosmology, including the Hubble tension, can potentially be addressed by modifying the physics that operated in the first few 100,000 years after the Big Bang. Early dark energy models, for example, propose that there was a brief episode of additional dark energy density in the early universe that has since faded away. This would slightly change the sound horizon, the standard ruler that DESI uses, which would alter the inferred value of the Hubble constant and potentially reconcile the tension between early universe and late universe measurements. Early dark energy is in some ways an even more radical departure from the standard model than evolving late-time dark energy, because it requires new physics to operate in the well-tested early universe, rather than just in the relatively poorly constrained late-time expansion. But it is a genuine theoretical possibility that is taken seriously by a significant fraction of the cosmological community. The fact that multiple theoretical frameworks can accommodate the observations is both strength and a limitation of the current situation. It is a strength because it means the anomalies point toward something potentially rich and physically interesting, rather than toward a complete breakdown of understanding. It is a limitation because the data we have is not yet precise enough to distinguish between these frameworks. More measurements are needed. Sharper measurements. Measurements that can test the specific predictions that different models make about the detailed shape of the expansion history and the detailed statistics of the galaxy distribution. This is why the next decade of observational cosmology is so consequential. DESI will continue operating and analyzing its full dataset of tens of millions of galaxies. Euclid will survey billions of galaxies over its 6-year mission, covering more than a third of the sky. The Vera Rubin Observatory will produce its legacy survey of space and time, cataloging tens of billions of objects in the southern hemisphere sky over a decade. The Nancy Grace Roman Space Telescope, a wide-field infrared instrument designed partly for cosmological surveys, will add yet another independent measurement of the expansion history using a different sample of galaxies and supernova. The Square Kilometre Array, a massive radio telescope being built in Australia and South Africa, will map the universe in the radio sky in ways that complement optical surveys together. These instruments will produce a convergence of measurements so precise and so independent that genuine discrepancies between them will be unmistakable. If dark energy is evolving, all of them should see it. If it is constant, all of them will confirm the standard picture. if there are systematic errors distorting current results. The combination of independent methods using different wavelengths, different tracers, and different calibration chains should identify and remove them. The process will not be clean or instantaneous. Big datasets take time to analyze. Systematic errors take years to identify and correct. The scientific community will debate the results as they come in. There will be competing interpretations, critical papers arguing for and against various conclusions, and occasional episodes of exciting hints that fade on examination. That is how science works on the frontier. It is messy and slow and frustrating and exhilarating in roughly equal measure. But at the end of it, the question will be answered: whether dark energy is what we thought it was, or something more complicated, will be a matter of solid, established fact rather than intriguing possibility, as a scientific matter are about as high as they get. In fundamental physics, there are a relatively small number of deep mysteries, problems so basic and unresolved that solving any one of them would represent a revolutionary advance in understanding. The nature of dark energy is one of them. What dark matter actually is, what caused inflation, why there is something rather than nothing, whether space and time are fundamental or emergent, whether there is new physics beyond the standard model of particle physics. These are questions that touch the foundations of physical reality. Dark energy is unusual among them in being simultaneously one of the deepest mysteries and one of the most immediately observable phenomena. You cannot see dark matter. You cannot recreate the Big Bang in a laboratory, but you can watch dark energy sculpting the large-scale structure of the universe in real time, galaxy by galaxy, light year by light year. Every night, the DESI and its successors operate. They are measuring it. That is a remarkable privilege for a species that has been doing systematic astronomy for only a few centuries. The fact that we have instruments sensitive enough to detect a 1% change in the strength of dark energy over billions of years, using the light of galaxies so distant that the universe was less than half its present age when they emitted it, is an achievement that would have seemed like fantasy to any physicist working even 60 or 70 years ago. The technology, the mathematics, the computing power, the institutional collaboration required to do this science at the level it is now being done, none of it existed within living memory of most people alive today. It has been built piece by piece by generations of scientists and engineers working across decades. The 5,000 robotic positioners in DESI, each moving to its assigned galaxy target with an accuracy of microns over and over across thousands of nights, are themselves a kind of poetry in metal and software, a machine designed to read the history of the universe, written in the colors of ancient light. And all of that effort, all of that ingenuity, all of those lifetimes of work has produced a dataset that is now telling us something unexpected. Not something wrong with the instruments, not something wrong with the mathematics, something possibly wrong with the universe as we understood it, the most important invisible force in the cosmos. The thing that controls the destiny of everything that exists may not be what we assumed, may be doing something we did not expect, may be writing a different ending to the story than the one we had composed. We can sit with that uncertainty, honestly. We can acknowledge that we do not know, while also noting that not knowing and having no leads are are very different situations. We have leads. We have strong hints. We have theoretical frameworks. We have better instruments being built right now. The not knowing has a shape, and the shape of the not knowing is pointing toward something in 2026. Cosmology finds itself in one of those moments that physicists and historians of science describe as a pre-revolutionary state, a state in which the dominant paradigm, lambda CDM in this case, is doing remarkably well overall, fitting almost everything we observe, but is accumulating tensions at its edges that it cannot quite resolve. The anomalies may dissolve. They have before, but the instruments bearing down on them are better than anything we have had before. If the anomalies are real, we will know within the decade, and if they are real, the next version of cosmology, the framework that replaces or extends lambda-se, will incorporate new physics that currently sits at the very edge of our theoretical imagination. Whatever form that new physics takes, it will have to explain three things that lambda CDM currently cannot explain. Why does dark energy have the extraordinarily small value it has rather than the enormous value that naive quantum field theory predicts? Why does dark energy have roughly the same density as matter right now, at this particular epoch in cosmic history, rather than being wildly dominant or wildly subdominant? This is sometimes called the coincidence problem. And if dark energy is indeed changing, what is the physical mechanism that makes it change? And what are the detailed predictions of that mechanism for the expansion, history, and growth of structure? These are hard questions. They have been hard for a quarter of a century, but hard questions with clean data tend eventually to yield. The dark energy mystery has been resistant, partly because the data needed to test. The most interesting possibilities was so difficult to collect. The DESI survey represents the first time we have had data of the quality and quantity needed to begin discriminating between the simplest model and its alternatives. The surveys that follow DESI will have even more data. The hypothesis space will narrow, and somewhere in that narrowing, the universe will reveal what it is actually made of, and where it is actually going, and how the longest story imaginable actually ends. We just have to keep watching. There is something worth dwelling on in the scale of what the DESI collaboration represents as a human endeavor. Independent of the scientific results, 900 scientists from over 70 institutions across more than a dozen countries, observatories, universities, national laboratories, computational facilities, all coordinating over a span of years to answer a single question. Science at this scale is relatively new. For most of human history, scientific knowledge advanced through the efforts of individuals or very small groups. Newton developed the laws of motion and gravity largely alone. Faraday discovered electromagnetic induction working in a small laboratory. Even Einstein derived general relativity in relative intellectual isolation, famously spending years thinking through the problem on his own. The idea that answering a fundamental question about the nature of the universe might require a consortium of 900 researchers with a budget of many tens of millions of dollars and a 5-year observing program would have been incomprehensible to scientists working even a century ago. This shift toward large-scale, collaborative science is one of the defining features of 21st century fundamental research. It reflects the reality that the easy discoveries have been made. The questions that remain open are hard, and answering them requires instruments so large and expensive that no individual or institution can build them alone. It also reflects the deepening connections between fields. The DESI team includes not only astronomers and cosmologists, but particle physicists, statisticians, computer scientists, engineers, and specialists in the precise calibration of optical systems. The data collected by DESI's 5,000 fibers is processed through pipelines involving millions of lines of code, checked against simulations that model the evolution of the universe from the Big Bang to the present day, and analyzed using statistical methods borrowed from machine learning, signal processing, and Bayesian inference. The sheer computational scale of modern cosmological surveys is itself a kind of staggering fact. The DESI data pipeline processes spectra from millions of galaxies. Comparing those observations to theoretical predictions requires running detailed simulations of the universe hundreds or thousands of times. Each simulation tracking the behavior of hundreds of billions of simulated particles across 13.8 billion years of cosmic evolution. Each of those simulations, run on some of the most powerful supercomputers in the world, may take days or weeks, and they have to be run enough times to fully sample the parameter space, to understand not just the best fit model, but the full range of models consistent with the data. Modern cosmological inference is, in a very real sense, a computational science as much as an observational one. This matters for understanding why scientific results like the DESI findings take time to confirm, and why the community is careful before declaring a discovery. It is not just that the measurements themselves are uncertain. It is that the chain from raw photons collected on the mountain to a claim about the behavior of dark energy passes through an enormous number of steps, each of which has to be validated, checked for systematic effects, and compared against alternative analyses. The blinding technique that the DESI team used, hiding their own results from themselves while analyzing the data, is just one example of the methodological care required. The team also ran extensive tests using simulated data, applied multiple independent analysis methods to the same dataset, and compared their results against previous surveys before releasing any of their findings publicly. This methodological rigor is sometimes invisible to the public reading science news, which tends to present results as either true or not true, discovered or not discovered. Real scientific results are more nuanced. They have statistical significances and systematic uncertainties and dependency on modeling assumptions. The DESI result sits at 3 to 4 sigma. That is a number that carries real meaning. It means the team has done their job well enough to exclude a null result with high confidence. But it also means there is enough uncertainty remaining that the result should be treated as a strong indication, rather than a final answer. The scientific community's careful language around these results, calling them hints and suggestive signals rather than discoveries, is not false modesty. It is an accurate description of what the evidence actually shows. All of this methodological carefulness is also, in its own way, a story about what makes science work. The tension between wanting to announce an exciting result and wanting to be certain that the result is right is one of the central human dramas of frontier research. Careers are affected by what gets published and when. Funding follows results that sound interesting. The temptation to interpret ambiguous data in the most exciting way is not trivial. Institutional pressures, the desire for priority, the excitement of potentially being the first to find something important. These forces are real, and the history of science includes examples of results announced too confidently, too early, that had to be walked back when more data or better analysis showed them to be artifacts. The flip side is also true. Waiting too long to report a finding out of excessive caution can mean that important insights are delayed for years. The supernova discovery in 1998 was checked and rechecked exhaustively before publication, precisely because the implications were so extraordinary. The teams were right to be careful. But if they had waited for what physicists now call 5 sigma certainty before publishing, the result might have been delayed by another full observing season. In fast-moving science, these timing decisions matter. The DESI team appears to have struck a reasonable balance. They published their first results when the signal reached a level of statistical significance worth reporting, while being explicit about what it was and was not. They continued to analyze more data. They invited scrutiny from the broader community. They engaged directly with critics who questioned specific aspects of the analysis. That kind of transparent, ongoing scientific dialogue is exactly how frontier science is supposed to work, and the scrutiny has been genuine. The suggestion by George F. Statheu and colleagues that a calibration offset in one of the supernova catalogs could explain the DESI signal away is not a frivolous objection. It is a real concern based on a real analysis. The DESI team has acknowledged it. The cosmological community is actively working to determine whether the offset is present, and, if so, how large it is and what it implies for the dark energy measurement. This is science resolving its own internal tensions through more measurement and more analysis, which is the only way it can. The broader picture that emerges from all of this is of a field in healthy, productive tension with itself, not a field in crisis. Not a field that has found something so fundamentally broken that the whole edifice is at risk of collapse, but a field where the most precise measurements ever made are beginning to strain the simplest version of the standard model, and where the community is responding with a combination of skepticism, enthusiasm, and the determination to collect more and better data. That is what scientific progress looks like from the inside. It is rarely clean or sudden. It is usually a long accumulation of measurements, arguments, and counter-arguments, gradually resolving into clarity. The resolution, when it comes, will be part of a longer arc in physics that extends well beyond cosmology. The question of what dark energy is connects to the question of why the vacuum energy has the value it does, which connects to the deepest unresolved problem in theoretical physics, the problem of reconciling quantum mechanics and general relativity into a single coherent framework. These two pillars of modern physics, each extraordinarily successful within its own domain, are mathematically incompatible. When you try to combine them directly, you get nonsense. The calculation that produces the absurd overprediction of the vacuum energy is a symptom of this incompatibility. A real theory of quantum gravity would presumably give a finite, sensible answer for the vacuum energy. The fact that we do not have such a theory is the same fact that leaves dark energy unexplained. String theory, loop quantum gravity, causal set theory, and other approaches to quantum gravity each offer partial frameworks for thinking about these questions. None of them has produced a complete, testable prediction that has been confirmed by experiment, but each of them makes different predictions for things like the detailed behavior of dark energy over cosmic time, the properties of primordial gravitational waves, and the statistics of quantum fluctuations in the early universe. As cosmological measurements become more precise, some of these theoretical frameworks will be constrained or ruled out. Others may find unexpected support. The universe is the largest laboratory available to us, and it is running an experiment right now that no human-built collider could replicate in this sense. The DESI findings are not just interesting cosmological news. They are a probe of physics at the most fundamental level that exists. If dark energy is evolving because of a scalar field rolling down a potential, the shape of that potential is information about physics at energy scales we cannot directly access in any laboratory. If dark energy is evolving because general relativity breaks down on cosmic scales, that is information about the structure of space-time itself at the largest scales it is possible to probe. And if dark energy is constant after all, and the current hints dissolve with more data, that is also a result of profound significance, because it deepens the mystery of why the cosmological constant has the exact small value it has, and puts even more pressure on theoretical physics to explain it. Either way, we learn something. Either the universe is telling us it is stranger than the standard model, or it is insisting that the standard model is essentially correct, but still inexplicably fine-tuned in ways we cannot explain. Neither answer is fully satisfying. Both answers are scientifically rich. The universe, it turns out, does not owe us comfortable conclusions. What it does give us, every clear night, is more light. More photons that have traveled for billions of years through expanding space, carrying in their wavelengths a record of the history of the cosmos. DESI collected them in its 5,000 optical fibers. Euclid is collecting them now. Vera Rubin will collect billions more, each one a tiny data point. Each data point part of a picture so large that no individual human mind can hold it all at once. Only the collective effort of hundreds of scientists and thousands of computers assembling and analyzing the data can begin to read what the universe is writing. That is the work of cosmology at the frontier. That is what those 900 scientists have been doing in the Arizona desert and in offices and data centers around the world for the years it took to build DESI's map. And that is what the scientists who will spend the next decade analyzing the results of Euclid and Vera Rubin will do. Reading the light, following the evidence, trying to understand as clearly as it is possible to understand what the universe is made of and what it is doing. The universe is approximately 13.8 billion years old. It will continue to exist in some form for a time span so vast that the entire past history of the cosmos, from the Big Bang to today, would be an invisible rounding error compared to the future. In all of that future, whether it freezes or tears or crunches, whether it cycles or simply ends, the only moments in which the universe could be studied from the inside by curious, measuring minds are the moments when stars exist, when planets exist, when chemistry has had time to give rise to biology, and biology to intelligence. We appear to be living in one of those moments. And in all of that enormous span of time and possibility, we happen to be alive right now, when the question of dark energy can be asked, when the instruments to probe it exist, and when the answer is just beginning to come into focus. That is a fact worth noticing. Whatever the answer turns out to be, the light from the most distant galaxies in Desi's survey left its source. When the universe was a fraction of its current age, when the Milky Way was still forming, when our sun did not yet exist, when the atoms that would one day make up every living thing on Earth were scattered across the void in the form of gas clouds yet to collapse, that light traveled for billions of years through an expanding universe, stretched by the very expansion it was sent to measure, and arrived at a mirror on a mountaintop in Arizona, where a machine turned it into a number that a human being read and thought about. That chain of events, from the emission of a photon in a young galaxy to the reading of a redshift by a scientist in a laboratory, is one of the most extraordinary things that has ever happened. And it is happening millions of times every night. The largest map of the universe ever made is a human artifact, built from billions of those moments. And it is telling us that we may not have been as certain about the future as we thought, that the force carrying us toward that future may be more surprising than we assumed, that the ending, whatever it is, has not yet been written in any language we fully understand. That is not a failure. It is a beginning. And perhaps that is the most accurate description of where cosmology stands in 2026. At a beginning. Not at the end of understanding, but at the start of a new and deeper kind of questioning, armed with better instruments than any previous generation. Studying a universe that continues to be more interesting than any model we have built to describe it. The map is the largest ever made. The question it is asking is the oldest there is, and the answer is still beautifully open. The universe does not owe us comfortable endings, but it does keep giving us more light to read,